Hey everybody, welcome back to Algebra 2 online. So today the plan is to talk about something called a matrix, and it is not the movie, which has stolen that term. It was a math term long before. But basically a matrix is just a lazy math tool we use when we want to solve systems of equations really easily. So up to this point, I've just been having you solve systems by hand, and sometimes people still do things by hand because it's quick at times, but there's a lot of problems out there where actually you have something like 17 unknowns and 17 different linear equations, and you want to use a matrix to solve it because a computer can do it really quick. So a matrix is literally like a table form of a system of equations, and these are just like three examples I have here. So there's sort of, typically you'll see these tables drawn with like a square bracket. You won't always see like a little line here. Sometimes it would just be literally nothing and then just the other row. They put the line in sometimes to help you kind of remember that there's like an equal sign there. But basically, you should see a pattern here. 7x, 7, negative 5y, negative 5, 1, 1, 8x, 8, so on and so on. And so basically, they're just taking the variables and the pluses and minuses and equal signs and kind of just dropping this stuff and storing it in here. And you have to understand that the first column is the x's, second is the y's, and this is always just the number. So again, here's another one. You can see the negative 4 and 15, the 1 and negative 4, and then negative 2 and 5. If these were just your three equations, then it would actually look like this. You would actually put little zeros in there as placeholders, because you don't just want like 1, 1, 1, and then 3, 4, 5. You need to say 1x plus nothing else in y and nothing else in z is 3. Nothing in x plus 1y plus nothing in z is 4, and so on. And basically what these are useful for is that we can use a tool on our calculators to actually get maybe like a messy form matrix like this and turn it into something like, I'm just making this up, so I have no idea if this is correct, but something kind of like this one, where we're going to be able to do something really quick on our calculator, and then we can read from this table that x is 2 and y is 3, and it'll just give us the solution to the original problem. It's basically a technology kind of just shortcut to solving systems is kind of how I just want you to think about it. So again, a matrix, not the Matrix movie. This is a tool so actually we have, there's a course here called Linear Algebra, and it's our highest level class that we teach. And linear algebra is actually where we study the theory of like matrices, which is like plural for matrix, and a lot more in depth and everything. But like I said, they're really just a representation for a system of linear equations in the nth dimension. So basically you can have as many rows and columns as you need in those tables. And the nice thing is, because you can when you do systems of equations here, you can add or subtract and multiply these different equations together in order to help you solve a problem. You basically then are allowed to add, subtract, and multiply matrices. There's also some weird things. There's something called a determinant. If you take Calc 3 here, you'll learn about determinants with me. There's something called the transpose, which is unique to matrices, and you don't really learn about that until this linear algebra class. But there's other things too. But these are some of the other unique kind of computations for a matrix. But really today, like I said, we're going to just use our calculator and use it as a way to sort of check work for a system of equations. And to kind of motivate this, I wanted to just do another example by hand, and then I'll show you how fast it is basically on your calculator. So if I was given these three systems of equations, the first thing I'm seeing, I got these 12s here and here, I guess. But I could add these two top equations and eliminate x. So I think that's what I'm going to do. So if I add these two, I would get 66y and then minus 24z equals negative 8, because the 12x's go away. And so that's going to be one of my equations I'll use. And then if I take a look at these other two here, if I multiply the, so I want to get rid of the x, so I'm going to multiply the middle equation by 3, and then I'll get the x's to basically be eliminated. So if I do that, bring it down here, so negative 36x, I'm going to have 144y, and then we're going to have minus 36z and negative 21. And then just going to copy that second equation, or third equation on the bottom here. Okay, so then I want to minus these equations to get rid of the x's. And then 144 minus a negative 6 would be 150y. And then negative 36 minus 42 is negative 78z. And then negative 21 minus 5 is negative 26. Okay. So now if you're looking at these two equations, one thing I'm seeing is that everything is even, here, 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 and here, here, here. So I'm going to call this equation 1, and I'm going to call this equation 2. So I'm just going to divide them by 2, because it's not going to affect the answer at all. I can do that. So equation 1 divided by 2 would be 33y minus 12z equals negative 4. And then equation 2 divided by 2 would be 75y minus 39z equals negative 13. And that just makes it like a little bit easier to do the system from here. This thing kind of looks like a 1. That should be a 39 right there. Okay. So then you just solve a system of two equations. And this is one where it's not particularly easy in either way. I would probably just take, what color do I want to use? It's fine. I'm just going to take this one and multiply it by 39. Take this one, multiply it by 12. And then I would get 1,287y minus 468z, and then it's going to equal negative 156. And then if you multiply this one by 12, you get 900y minus 468z, and then you get negative 156. So if you wanted to eliminate z, you'd have to subtract, right? So that would get rid of that. And then 1,287 minus 900 is 387y. And this is kind of nice because when you subtract over here, you also kill the numbers, which is going to make this really easy. So then we just get that y equals 0. And then we could go back to maybe I'll plug into this equation right here. So if you plug into that, 33 times 0 minus 12z equals -4, it's going to tell you z is a third. And then you can just go back to any equation up here with your y and z and get x. And I'd probably do the first one. So if I plug into the first one, 12x plus 18 times 0 minus 12 times a third equals -1. If you solve that out, I know you just get a quarter. So basically, you're getting a solution of 1/4, 0, third. So this system of equations, this is three planes, and those three planes intersect at this point. So now I'm going to show you a really, really fast way to check your work. And I still want to see that you can do all this algebra, but I am going to be totally fine if you use your calculator to check your work here. So I'm not going to read this to you because you can just pause the video and read it, but basically this is how you'll do it on a TI-84. If you have like an Inspire or a TI-89, something like that, then I can show you how to do it like one-on-one. I actually have like an emulator software that I can pull up in class, and I can show you how to do this kind of stuff in class too. So pause, read this over, and then I'm going to do that on my own here, and I'm going to do it actually for this problem, and I'm going to show you the answer. All right, so when I went through those steps on the next slide there, what I got out was 100.25, then I got 0100, then I got 001, and then this 0.3333 thing, just forever and ever and ever. So, we already know the answer, but what this means, this is a really quick way. It took me maybe 10 seconds to plug this stuff into the calculator. And again, I can show this in class if people want me to. But basically, you have 1x equaling 0.25, which we got. You have 1y equaling 0. And then you have 1z equaling a third. So this is like a really quick way to just check that what we got really is the answer. All right, so I wanted to do some weird kind of cases. So if you plug in to the calculator and let it do the RREF thing to this, you will get on this one 1000, 0110, and then 0001. And on this one, you would get 107, -3. And then 0, 1, 2, and -2.3 repeating. And then you're going to get a row of zeros. And both of these kind of represent weird cases. And this one, probably a little more clear is my guess. So this says here that x equals 0. Then it's saying y plus z equals 0. And then it's saying at the end 0 equals 1. And really, this is the giveaway. This right here means it has no solution. So you can check no solution cases even with this, because you're going to get a row that makes no sense, like this. You probably have an idea where this is going, because I said this is some weird cases. And the other weird case is when we get things like a row like this. So that last row here, this thing just means basically 0 equals 0. And if 0 equals 0, that is like a true statement. And so you're getting an infinite amount of solutions. Again, remember, doesn't mean all real numbers, because really what it means is the planes intersect on like a line. So you might have I'm not a good artist with this stuff, but it's like there's some line, and that line is basically in two different planes. So it could be in and I guess the red one could go down if you understand what I'm trying to draw there. So it's like there's like this cross I'm trying to draw right here, but this line of intersection is like in both planes. So if you see this, if you see a true statement, then it's infinite solutions. It's like they intersect on a line. Or it could be intersecting even they're like the same plane. Like you could have one plane, two plane, three plane. That one I can draw. So, that case or the line case are both infinite solutions. And then you can definitely have this where you have something that's not true, and that would just be a no solution case. So the last few things I want to show you quick are how we can like add and subtract. So this shouldn't be too surprising because if you have like linear equations, you can add and subtract, when you do like elimination or something. And it's really no different with matrices. So you can add and subtract like if and only if though they have the same dimension. And it literally is just done component-wise. Like this is your x's, your y's, and like the number, right? So you can add this x to this x and get a 6. Then you can add like this y to this y and get negative, maybe I should color code a little bit. So those added to give me 6. This adds to negative 8. This adds to get 8, right? And the bottom row would just be, 5, 10, 1, using like the same idea. But you just add component-wise, 5, 5, 1, 0. But it doesn't make sense if they're not the same size. Like here, you would literally just say no solution because they're not the same size. This is actually what we would call a 2-row by 2-column matrix. This is a 2-row but a 1-column matrix. These ones, not that it really matters, but this is 2 by 3 and this is 2 by 3. It's always rows, then columns. But since this 2 by 1 is not the same as a 2 by 2, or since this is not 2 by 1, then you can't add them. And that's same with subtraction too. And subtraction works exactly the same as you would think. Probably like if it was 2 minus 4, you just put negative 2. And you can do, stuff like this because if you can add and subtract, you can kind of like solve for x. So, what I would do here is I'd probably add that over and then take this matrix and I would subtract it to the left. So I would get x equals negative 3.4, negative 5.2, then 8.1, 2.7, negative 6.4, 3.9, that thing, and then minus the blue one, which is, I'm going to do that, the blue one, which is 4.3, negative 3.5, 1.2, negative 2.8, 4.3, negative 1.9, and then you can literally just do subtraction component-wise. So you can do, to get x here, we can just do negative 3.4 minus 4.3, and we'd get negative 7.7. Then if you do negative 5.2 minus a negative 3.5, you'll get negative 1.7. And I'm just going to fill in the rest because you probably get it by now. So there's things in, like these linear algebra courses I was talking about where we're like solving for a matrix that does a certain thing. And you still should always be thinking about it as like, these are like the x's, the y's here, and this is just like the numbers that those lines equal. So multiplying by a scalar is fine as well. So you can do like the number 3 times a matrix. It's basically just like an elimination when you solve, we did one, let's just go back really quick. So we did basically this here. We can multiply a linear equation by something And we also took a linear equation and we divided it to get to this. So we can multiply by scalars like that, and that's fine. And it literally, again, just goes component-wise. 3 times 2, 6. 3 times 0, 3 times 0, 0. 3 times 7, 21. 3 times negative 4, negative 12. And then we'd have 15, and then we'd have 3. There is something where we do matrix multiplication. So we can do like a matrix A, let's say, times a matrix B. You can have something like matrix A being like 1, 2, 3, and you could multiply it by like negative 3, 2, 7, 1. This is actually much more complicated and would take a lot longer to explain. And I will actually be posting some videos that kind of give you a place to look at if you want to know more about this. This is truly gets into some like real linear algebra material, and it's very, very, very unlikely that there would be anything in this class or pre-calc or SATs or any of that stuff where you need matrix multiplication like this. This is definitely important, but multiplying a matrix by another matrix is a little more complicated than we really need right now.